Okay, today's problem 141, linked list cycle. It's quite common. I saw it last time. So basically, we are giving the list of linked list, basically list nodes, and we have a list of them, list of linked list nodes. And given this structure, we have value and we have next node, and this link this linked list might have cycle, or like, yeah, it might have cycle. So it might have like the next element might have be like cycled to their previous one. And the task is to figure out if this linked list has a cycle. So the idea is the first one, there is a complication here. We have 10 to the 5 number of nodes, and this position, pause, pause. Mhm. Okay, so this is a task, and the complication is to follow up how to solve this in O of 1. So first of all, let's think about how we can solve it in O of n with space complexity. So I'll do the following. We have a let's say a linked list. We have 1, 2, 3, and then let's say have 5, and then cycle to 2. In this case, I'm gonna go one by one on the list, and then I'll save the nodes into array, possibly array list, and then, or probably in a hash set. And if the value already, like node value already is inside the hash set, next node value is inside the hash set, means that there is a cycle. If we finish the going through the array and we didn't find through the list, and we didn't find the previous nodes in the next node, then it means that it is this list doesn't this linked list doesn't contain a cycle. So let me quickly do this. So I have this one. Let's say we use Java here. Uh, we have this and this. If the list node, let's make it inside. Let's put it inside, and let's start programming that one. So we need to find if. Okay, so it was like this, like this, like this. And then we need to implement this function. So the first idea is to have hash set list node, then import hash set nodes equal new hash set, and then we have while I would say you have list node current equals head, and then while current not null, we do this current equal current next, and then we do that if nodes contains, let's say find. I don't know what we have hash set API. Let's say find check hash set find okay contains hash set if nodes contains node let's say current node, let's say current car car. If node contains current, then we're gonna return true. Else we're gonna add nodes, add car, and then current equals current next, and then here return false. That's it. Okay, let's check on a couple of examples. So we'll have, if you have this head 3204, then we have cycle. So let's say you have 3204, and then 2. And here it's errors. So if you do like this, what we'll have, we have nodes, current equals head, so current equals 3. It doesn't include into it's not included into nodes, so we'll have the variable nodes equals empty array. Doesn't include, it's not included into the hash stat node, so we're gonna include it. And we move to the next one. Next one is not included in the nodes. We add it and move to the next. Next one gonna be 0. 0 is not included. Move next, add and move next. 4, we check 4, is it included? No. We add it and move next. So 2 now. We check if node contains current. It contains here. And we return true. Okay, that's it. Let's quickly check. Current. Say current. And yeah, so runtime 12%. Accepted. So the next challenge is to basically solve it without this hash set. So time complexity is like whatever we have number of nodes, but the space complexity we have often space complexity, whereas n is number of nodes, and we wanna remove that by probably trading time space complexity for time complexity for space complexity. So we need to make it O of one, and it's basically done through this logic. We have like fast, fast. Let's say we have like red gonna be fast pointer, and let's say brown gonna be fast pointer, and then green gonna be a slow pointer. And for the fast pointer, we're gonna move it um, two elements at a time, two nodes at a time, and a slow pointer gonna move like one node at a time. So we do the first move, we move um, slow pointer one to the next element, and we move fast pointer to the two elements. So one, two, and we check if the fast pointer equals slow pointer. No. So we move next. Um, we move. So this is the current state. So we move fast pointer one, one, two, and we move slow pointer. Gonna be just one. And check again. You does they do they match? They don't match. So we do that again. We move a slow pointer one cell, and we move fast pointer. Also, fast pointer moves two nodes at a time. So it was here, and it jumps here, and the three, and then it jumps on the five. So we have fast pointer here, and we check if they match. Yes, they do. So let it be. There is also interesting thing because they didn't match in. Oh, yeah, I know. So we need. So they matched, and in order to find their actually the cycle where it's like started, uh, we need to continue going one, but now like not two, like two at a time for the fast pointer. We need to go one at a time for the fast pointer, and we need uh, to kind of now we have like just two plain pointers. First pointer starts an intersection point, and a second pointer starts at the beginning, and we move them one at a time. Uh, like we move them both every step by one node. So this pointer moves here, and this pointer moves here. So as soon as they intersect, it means that the node that caused the cycle, where basically the cycle um, kind of started. So you see that cycle, so it back references to two here. So it means that basically that's the node where we have this branching. All other nodes have only one incoming and one outgoing link. But this node has two incoming, like this and this, and one outgoing, like this link. Yeah. So that's it. I'll try to code this one. I'll code that one. So this approach gonna be something like that. We're gonna have a list node fast equals head, and then a list node slow equals. Sometimes it's called this slow is called turtle or tortoise, and the fast is called like hare. This is a famous song about turtle and a hare, where they compete against each other. So the slow one gonna be head also, and then while and then let's say we have head, let's say slow gonna be next, and then fast gonna be next, and if fast equals null, I'm gonna return false, else we need fast equals fast next. And then while fast not equals slow, we gonna continue this procedure. Fast equal fast next. If fast equals null, we're gonna return true. Then gonna fast equals fast next, and then slow equals slow next. And then, yeah, we need to return. And again, if fast equals null, then it means that the end of the, so here you should return false actually, false, and then here false, and then here you should return true, because we found a meeting point for the fast and slow pointer. But here we just fast pointer moves faster, that's why we need only to drag it, and we need to double check every time we move the fast pointer to next cell. We need to check if the next cell is null. If it's null, it means we at the end of the linked list and there won't be any cycles. So that's it. So the space complexity of this is gonna be of 1, but the time complexity is pretty interesting. So we need to calculate whatever path the hair like runs around the cycle so that they meet with the tortoise, with the turtle. It might be harder than I think. So I guess we need to, in order to do that, you first need to prove that this algorithm works, and then you can like basically like calculate. So you can denote this one as x, this distance as let's say this distance as y, like cycle distance, and yeah, something like that. So let's check the solution. Okay, let's check here. False. Submit. If fast equals null, return false. What does it? What that? Oh, runtime error. Can't read. Next. Ah, list node. Head next. Ah, okay. If head equals null, it to return false. That's actually a good example. Yeah, probably on some of the interviews. Cannot read next. What? Where? Line 22. Okay, need more extra checks. Okay, so that's it. Gonna wrap up. So it's pass.